Welcome. In this video, we're going to introduce mathematical induction. So we'll start with the principle of mathematical induction. So what we're going to do is start with a statement, and that statement is going to be about the integers. So you can dream up any statement that you possibly might like about the integers and try to show that it's true with mathematical induction. Many statements that we might be talking about in mathematics would be an equation. An equation is a statement. The statement is that the left-hand side equals the right-hand side. But the statement doesn't have to be an equation. It could be something else, like it's possible to tile a certain shape with a certain number of objects. Or it could be about a sequence of numbers. We're guessing that the sequence of numbers works out this way, and we can prove it with mathematical induction. So if you ever have a guess at a particular formula or a particular pattern that's repeating about the integers, mathematical induction is a wonderful tool to get us started trying to show that your guess is correct. Okay, so in this example, we're going to try to prove that consecutive integers, when added together up to the number n, give you n plus 1 multiplied by n divided by 2. And we're going to do this with mathematical induction, which means we have to do a base case and an inductive step. So in the base case, we just have to show that the smallest case scenario is true. So P is my statement, and the subscript B is saying I'm going to start at B. The integer B is the smallest case scenario. So for this example below, the B is determined by n being bigger than or equal to 1. 1 is the smallest case scenario that I need to look at. So in our example, the base case, we'll write BC for short, is occurring when n equals to 1. So I always like to write down what I want to do with my base case. So what I'm trying to do here is show P sub 1 is true. So if we successfully show that we can plug 1 into this equation, then our base case is proven. So let's go ahead and do that. Let's plug in 1. So the left-hand side would be 1 plus 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 all the way up to just 1. So it's just 1 on the left. And then if we plug in 1 on the right, we would get 1 plus 1 times 1 all divided by 2. So that equals 2 divided by 2, which is also 1. So our base case checks out. We've successfully shown that P sub 1 is true. So I'll write down, therefore, P sub 1 is true. And we can move on to the inductive step part. So in the inductive step, we're going to show that P sub n gives you P sub n plus 1. In other words, if we start at 1 and we know that 1 is true, then we can use that to conclude that 1 plus 1 also gives us a true scenario of our statement. So P sub 1 would give us P sub 2. And we're going to do this for every n that's bigger than the base case. So what we'll end up with is a chain reaction in the inductive step, where 1 gives you 2, 2 gives you 3, 3 gives you 4, and so on and so on and so on. So let's get started with our inductive step. So I'm going to write down IS for the inductive step, and I'll again write down what we're trying to do in the inductive step. So here I want to show P sub n implies P sub n plus 1 for n values that are bigger than or equal to 1. So just to make things really clear, the original equation that we started with, this is my statement. That statement can have n equal to 1 plugged in, 2 plugged in, 3 plugged in, any integer you like, bigger than or equal to 1, according to the problem. So this equation is my statement. So I'm going to write p sub n colon to describe that. Another way of writing down this statement is p sub n, or p sub n is defined as this statement. Okay, so how are we going to accomplish this goal? So let's give ourselves some space. In the inductive step, we want to show an implication is true. So my implication will be true when I can conclude that p sub n plus 1 is true. And I get to use p sub n to help me along the way to get there. So let's write down what we want to do in terms of showing p sub n plus 1 is true. I want the left-hand side to be 1 plus 2 plus 3 plus dot 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 all the way up to n and n plus 1. What I'd like to do with that expression is get it to equal n plus 1 multiplied by n plus 2 all divided by 2. Notice what we've done is taken the original equation and replaced, everywhere we saw n, we replaced it with n plus 1. So the n became n plus 1 on the left-hand side, and the top here became n plus 1 for an n plus 2, and that n there became n plus 1. So that's why I wrote down the numerator below as n plus 1 multiplied by n plus 2. So our job is to make these two expressions equal each other, use logical steps to get these two expressions connected with a chain of equality. And also remember, we're allowed to use p sub n along the way. I think that's where we're going to start. Notice that the left-hand side of p sub n is sitting right there. That is p sub n. So I'm going to write a little p sub n over top of my equality symbol to let us know that something special or extraordinary occurred here, because the right-hand side, of course, of p sub n can replace the left-hand side. So my left-hand side would be n multiplied by n plus 1 all divided by 2, and we'll carry the n plus 1 from above. So next up, the expression that we just wrote down is equal to n plus 1 factored out of both of the terms from above. So we can take n plus 1 and write a big bracket, and then what's left inside is n over 2 plus 1. And as one last step, we're going to factor out 1/2 from the big brackets. So n plus 1 is now over 2, and then inside of the big brackets, we're left with n plus 2. And writing all of this expression as one numerator and one denominator gives us the final result that we were looking for. So that last step was our goal, and each of the equality symbols along the way have a very good reason for them. The first one is from p sub n, and the next three are regular algebraic moves. So in conclusion, we now know that p sub n plus 1 is true. So therefore, p sub n plus 1 is true. And that completes our induction. So in the inductive step, we used p sub n along the way to help us conclude that p sub n plus 1 is true. So in summary, I like to think of this as a domino effect. So you could think of P sub 1 as your very first domino. So let's say you're lining up dominoes and your first domino is P sub 1. Your next domino is P sub 2. You line them up so that if P sub 1 falls over, then so does P sub 2. And you line up P sub 2 so it knocks over P sub 3, and so on and so on. Dot, dot, dot. That process continues on and on and on. So in the inductive step, we show that all of the implications, all of the arrows that I just wrote down are true. So that is true, that is true, that is true, that is true, so on and so on and so on. And then in the base case, we show that P sub 1 is true explicitly. We just plug in the numbers or plug in the scenario and say, yeah, that's true in the base case. And because all of these implications are true, we now know that 1, when true, tells us that 2 is true. And that tells us that 3 is true. And that tells us that 4 is true, and so on and so on and so on. So it's kind of a nice effect to think of dominoes knocking over the next domino in that line. Okay, we're going to do one more problem in this video. It's an extension of the previous problem. So instead of starting at 1 and counting up to n and adding all those numbers together, we're going to allow ourselves to start at any integer, negative, 0, positive, anywhere you like, and we'll climb all the way up from that starting point to n again. And apparently that's supposed to equal this mess over here, n plus m all multiplied by n minus m plus 1 divided by 2. So that's what we need to verify. That's what we need to prove using mathematical induction. So a similar process from before. We're going to write down a base case. For our base case, we're going to plug in the smallest case scenario for n. The smallest that n can possibly be in this particular problem is the value m. So we want to plug in n equal to m for this case. So what are we trying to show? What is our goal to accomplish in the base case? We want to show that P sub m is true. So let's see if we can do that. Let's plug it in and see what happens. So on the left-hand side, we get the sum of m all the way up to just m. So it's just m on the left. And then on the right-hand side, we would get m plus m. Remember, we're replacing n with m. And then m minus m plus 1. That's my numerator. And then the denominator is just 2. So what we end up getting is 2m divided by 2. The 2's cancel out and we get m. So our base case checks out, and I'm going to remind ourselves, give ourselves the reward of writing down. Therefore, we now know that P sub m is true. Okay, now we're ready for our inductive step. Okay, so in the inductive step, we are going to show that P sub n implies P sub n plus 1. So P sub n implies P sub n plus 1, and we want to do this for all values of n that are bigger than or equal to m. So I'm going to set up our goal. I'm going to leave some space again and set up what we want to do. Okay, so we want the left-hand side of m plus 1 all the way up to adding up to n and including n plus 1. That's the left-hand side of P sub n plus 1. And we want to get that down to the result of n plus m plus 1 all multiplied by n minus m plus 1 all divided by 2. So what I've done is replaced the n with n plus 1 in my original expression. So if we scroll back up, that's my original expression, and everywhere I saw n, it got replaced with n plus 1. All right, so let's see if we can take on this challenge. The first m to n terms on the left-hand side are highlighted right here now in red. So for these terms, we can replace that with what p sub n says. So p sub n tells me that those red brackets are equal to n plus m all multiplied by n minus m plus 1 all divided by 2. And we'll copy the n plus 1 from above. Now our job is to find a way so that the two expressions that we wrote down so far are equal to each other. So right now we have that the original expression is equal to this by p sub n, and we have to connect it to the right-hand side of pn plus 1. So let's just look at the two expressions that we have and think about how they're the same and how they're different. Well, we have everything being divided by 2, and not everything here is being divided by 2. So how about we fix that by factoring out a 1/2 or making sure everything is being divided by 2. So I'm going to write another step that takes everything and puts it over top of 2. So n plus m multiplied by n minus m plus 1, and then we'll have plus 2n plus 2. That allows us to put everything over 2. Okay, so this is one step in the right direction. Now everything is being divided by 2 above, and everything is being divided by 2 below. We just have to make sure the numerators match. So the numerators do look a little bit different right now, and I'm noticing that the numerator below, down here, is in a factored form, and this one is a little bit more expanded. There's 1, 2, 3 terms above, and just 1 term below. So I certainly find it easier to expand terms rather than trying to factor them in some creative way. So I'm going to try to force the bottom part to look like the top part. And we're going to do this nice and carefully to make sure that, that the right terms get multiplied by the right terms. So I'm going to take my red pen and notice that there's an n plus m right there and an n minus m plus 1 right there. And if I was to multiply those two terms together, I would get this first term out of the 3 from above in the numerator. So I think that's a very good start to multiply those two red bracketed expressions below. So we would get n plus m multiplied by n minus m plus 1, and then n plus m multiplied by 1, so n plus m, and then 1 multiplied by n minus m plus 1, so n minus m plus 1 is my next term, and then finally 1 times 1 gives me a plus 1. So I expanded out the numerator. So now, what matches and what doesn't? We have n plus m multiplied by n minus m plus 1. The exact same term is right there. We just have to make sure the leftover terms equal what they're supposed to equal. So we have a 1 plus 1, and that's 2. So that part's great. And then we have a 2n above, and below we have an n plus n. That also makes 2n. And in addition, the m minus m cancels out. So the final equality is indeed verified. We have exactly what we're looking for. And I'm just going to indicate that the m and the minus m cancel out. And then our inductive step is complete. And what we are trying to prove is proven. So let's write down that concluding statement that just says, therefore, p sub n plus 1 is true. Okay, so we can use a little bit of an application of what we just proved to finish this off. So we'll find a closed form for the following expression. The expression has the consecutive integers added together on the top. So what we get is n multiplied by n plus 1, all divided by 2, out of the numerator. And then in the denominator, we have to use the formula that we just came up with. Let's remind ourselves what that is. Let's just scroll up for a moment. What did we just prove? We just proved that consecutive integers, when added together, will give you the largest number plus the smallest number multiplied by largest minus smallest plus 1. So let's write that down below. Okay, so back to where we were. The largest number is 2n, so I'll write down 2n plus n. And then that gets multiplied by the largest number, 2n, minus the smallest number, n, plus 1. And all of that gets divided by 2. So in the main numerator, we have a divide by 2, and in the main denominator, we have a divide by 2. So what we're left over with in the numerator is n multiplied by n plus 1, and in the denominator, we have 3n multiplied by 2n minus n just gives me 1n plus 1. So now in the numerator, we have n multiplied by n plus 1, canceling out with what's in the denominator. And what's left over, it's kind of really neat. This fraction always, no matter what n is, results in 1/3.